case you were not around for session 2, my name is Carly Pittman and I'm a civil engineer in our Edmonton office. I'll be moderating this session. Our theme for this session, session 4, is storm trunks. Our first presentation is on the City of Calgary Upper Plateau Storm Relief Sewer Project. Our presenters are Nadeer Lalji and Gabriel Jean. They're both from our Calgary office. Nadeer has over 18 years of engineering experience. He has inspected, designed, and led project teams for various trenchless installations, ranging from pipe ramming through tunneling. Nadeer led the project team that delivered the largest micro tunnel installation in North America at its time for the City of Calgary, and he's currently leading the design of a 3.4 meter diameter tunnel installation in the heart of Calgary. A fun fact about Nadeer is that he has seen the movie Frozen 5 times. This is either because he has a deep emotional connection to the storyline or because he has 2 daughters, and we will never know. Gabriel is a project engineer with over 13 years experience. His expertise is in municipal infrastructure design and construction, from the conceptual stage to construction completion. Gabriel is involved in various sanitary storm and water main installation projects and has a various interest in trenchless techniques. Fun fact about Gabriel is that he is an avid soccer fan, and he does not go to sleep without watching the late night show with Stephen Colbert. I had to Google that, but it's late, so good for you. You must be a super fan. So now I'd like to hand over to Nadeer, who's going to start their presentation. So go ahead, Nadeer.
Thanks, Carly. For the record, I believe it's Stephen Colbert.
Colbert? I Google.
No,
I don't know.
That, yeah,
I don't
the
like
pronunciation
soccer.
doesn't show up in...
Colbert. Oh, I'm going to put this back now.
As Carly noted, my name is Nadeer Lalji, and I work for Associated Engineering in our Calgary office. Before beginning, I would like to thank everyone in this session for joining us throughout the day and certainly for this presentation. I will be joined today, as Carly noted, by my colleague Gabriel Jean, also based in our Calgary office. Today, we will be speaking to you about a project known as the Northwest Inner City Upper Plateau Separation. We will be focusing on the trenchless options we evaluated to mitigate the issue at hand. I see that some of our City of Calgary clients are in the audience today, and it's a good chance to thank them for trusting us to take this challenging project on. For those of you who haven't been able to come to Calgary, this is what a week in Calgary can be like. This first picture was taken in October of 2020. This second picture was also taken in October of 2020. With that context of the project area, we will start our presentation with a brief background of the project, stating the problem we are trying to mitigate. We'll then briefly discuss the options that were identified to solve the problem, and then focus in on the trenchless options considered for the project. This is a large study area within inner city Calgary. It is located just north of downtown, north of the Bow River. The darker shaded area is referred to as the Upper Plateau. The lighter shaded area is referred to as the Lower Plateau. The Lower Plateau lies within the floodplain of the Bow River. The 2 areas are separated by approximately 35 to 40 meters in elevation. Within this study area, the Upper Plateau collects stormwater from an area of approximately 300 hectares with a peak flow of approximately 20 cubic meters per second for the design event. The Upper Plateau conveys stormwater via underground infrastructure that then runs through the Lower Plateau as storm ducts. However, the Lower Plateau's local stormwater system is also connected to the same infrastructure. As a result, when this system is overwhelmed, regardless of whether the runoff came from the Upper Plateau, the Lower Plateau is the area that incurs the flooding. As the Lower Plateau is within the floodplain of the river, This stormwater infrastructure is also exposed to varying river levels. The project that we're discussing today had a very straightforward objective: separate Upper Plateau stormwater from the Lower Plateau. It's a challenging objective to achieve, though, given that we're working within the inner city, and one we have been working closely with the City of Calgary to attempt to resolve. A number of years ago, we were fortunate enough to conduct a drainage study of this entire area. Within this drainage study, we proposed a design solution consisting of a large diameter storm trunk siphon installed via tunneling to convey the flow directly to the river before it could impact the Lower Plateau storm system. During the preliminary design phase of this project, the City of Calgary led a value management session during which multiple potential solutions were raised. An alternative conveyance route for the Upper Plateau flow was considered. However, this route required a much longer installation and required construction of large diameter storm trunk through congested residential areas. This option was deemed too costly and challenging to proceed with. Storage of the peak flow was also considered. However, the optimal location to implement this storage would be Riley Park, a highly valued public space with many recreational uses and no replacement areas in close proximity. This solution was not carried forward due to the significant social impacts associated with it. Two very different trenchless approaches were also considered. One was to utilize the existing storm ducts to convey the Upper Plateau flow directly to the Bow River while building a new collection system for the Lower Plateau. As Gabriel will touch on in greater detail, this approach would require pressurization of the existing storm ducts beyond what they were designed to withstand. This would require treatment of these ducts, shown in red, and replacement of portions of the duct, shown in yellow, and also significant construction within the Lower Plateau system to reconstruct the local collection system, as shown by the orange lines on the screen. The other trenchless option we considered was an optimization of the trenchless installation of a new storm trunk siphon to convey in Upper Plateau stormwater directly to the Bow River. The size of this line is hydraulically dependent, but would be approximately 3.4 meters in diameter to convey the design flow. As a result, this line would have to be installed as a siphon, as none of the available routes had the space needed to accommodate this large a storm trunk through open cut excavation. Deepening of the storm trunk at this diameter, and then with a length of approximately 750 to 800 meters, we considered tunneling and microtunneling as viable options. A little later on, Gabriel will discuss the specifics of these approaches we considered. At this point, I'd like to hand it off to Gabriel to continue on with the presentation.
Thank you, Nadeer, for reusing the existing docks as part of one of the options that Nadeer noted earlier.
Yeah, sorry about the technical delays here. We'll get this going here, and just appreciate a little bit of patience.
Thanks, as Jason noted. So when we considered treating the ducts, we looked at various options to line the ducts. And the reason we needed to do that is for any structural engineers in the room, the reinforcing at these upper corners wasn't designed to withstand internal pressure, certainly not to the extent that we would expect to incur on this system. And with this design. And the fact that these ducts are shallow also meant that there wasn't much soil loading above to resist the pressures we would experience. So we considered a cured in place approach, a spray lining approach, and a slip lining approach. Cured in place approach, I think some of you may know, but there are It consists of installing a lining, as you can see on the graphic, through the existing pipe and conduit, and then inflating that lining to adhere to the conduit itself. Okay, and the curing process would have it would have it adhere tightly to the conduit it's applied to, essentially forming a new conduit with a smooth interior lining. So with the alpha, we looked at a couple of different products here. We looked at an in situ form liner. We looked at an alpha liner, UV cured product. And certainly the products are very suitable in round conduits quite often. Our challenge here was that we have a square and a rectangular conduit to line, and the rectangular conduit was a particular challenge for this type of application, because when this particular application isn't meant to stretch horizontally, and what would result is a much smaller cross-sectional area in the conduit, and that conduit wouldn't be able to convey the design flow we needed. The opportunity we thought had a bit more promise was a spray lining approach. We consulted with many different spray liner outfits, and the two that had some promise and advanced conversations a little further were a Milliken geopolymer solution, and they distribute this out of the United States, as well as the Warren Environmental epoxy lining.
Sorry, everyone. Okay, where were we? Thanks a lot, Nadeer, for reusing the existing dock as part of one of the options that you mentioned earlier. We looked at CIPP, spray lining, and slip lining as trenchless methods. The photo on the right is from an inspection of the 1.3 meter by 1.3 meter double dock. The figure on the bottom left represents the 3 meter wide by 1.5 meter high dock. The first option we looked at was CIPP, cured and placed pipe. We considered in situ form, which uses hot water or steam to cure the lining. The in situ form installation would be suitable for the 1.3 meter by 1.3 meter duct, but not for the 3 meter by 1.5 duct. Another concern with the in situ form install is that it would not be a tight fit to the dock walls at the corners. The other CIPP option we looked at was from Alpha Liner. It is close to what the in situ form install is, but it uses UV light to cure the lining. It would provide a tighter fit to the dock walls, but as noted for the in situ form installation, it would not be suitable for the 3 meter by 1.5 meter duct. And this is just a picture of what the Alpha liner would look like. For spray lining options, we looked at a two-part epoxy application from a firm called Warren Environmental. We also looked at a geospray geopolymer from a firm called Milliken Geopolymer. These options, they look really promising, but the vendors that we talked to, they were not able to confirm that their products would work for this application. This is just a picture of what the geospray geopolymer would look like. For slip lining, going back to the slip lining side, for slip lining, we looked at glass fiber reinforced plastic pipes from companies called Channel Line and Ami Blue. We also considered a spiral wound pipe from Sekisui. The reduction in cross-sectional area from these options would not meet the project requirements. So early on, slip lining was not considered any further. For the dedicated line, we considered alignments on 10th Street, 8th Street, and 7th Street Southwest. The alignment on 7th Street with an outfall south of Memorial Drive was the one selected to progress with the design. We engage Turber Engineering to provide feedback on the soil conditions that will be encountered along the alignment on 7th Street. Turber conducted a field investigation and was able to characterize the ground as shown on this figure. From 10th Street to 2nd Ave, the bedrock is between 3 to 13 meters below surface. At 2nd Ave, it takes a significant dive. To reduce cost and minimize disruption to the community, we use this profile as a guide to consider various tunneling methods with a depth of 13 meter to 40 meter below surface. Shaft at 10th Street would be 20 meter deep, while the shaft at the outfall would be 13 meter deep. We first looked at an open face tunnel installation from 10th Street to 1st Ave Southwest, with the remaining installation done by pipe ramming past the transition between bedrock and overburden soil. The initial tunnel support would be segmental lining or steel ribs and lagging with fiberglass reinforced plastic pipe as carrier. Although the size of TBM will ultimately be left to the contractor, we estimate a 5.1 meter outside diameter for the TBM. This is just showing what the FRP would look like, as well as the steel ribs and lagging. The open face tunnel option has some challenges. We would need a shaft out at the cul-de-sac at 7th Street, north of Memorial Drive. The shaft would be close to houses and condo buildings. It would be noisy, even if measures would be taken to minimize the noise. The size of casing for pipe ramming would be challenging, as well as it would stretch the limit of what local contractors can do. We also considered a microtunnel installation with a 3.4 meter ID. The carrier pipe would be a concrete jacking pipe, seen here. The MTBM is able to advance in mixed ground conditions and would not require a change in method along the alignment. A 3.4 meter ID MTBM would push the limit for this type of application. A TBM with a pressurized face is also considered and would be suitable as well. After assessing all the trenchless options, our recommendation was for MTBM installation or TBM with a pressurized face. It offers limited disruption to the community, is suitable for mixed ground conditions, and can be completed by one contractor. With that, I will pass it back to Nadeer to conclude this presentation.
Thanks, Gabriel. So in summary, large-scale stormwater management in inner-city Calgary required us to examine two very different trenchless solutions. We considered repurposing infrastructure to convey pressurized flow, and that seemed promising. But as we delved into the details, it proved to be challenging and beyond the limits of what could currently be provided on the market. It turned out that in this case, tunneling and microtunneling was the appropriate solution. Certainly a project with this much complexity requires a number of people to be involved, and we've had the good fortune of working with many of City Calgary personnel very closely on this. In particular, Penelope Reed, the City of Calgary's project manager for the project, and then many associated engineering staff as well. And we've been supported on the project by Thurber Engineering and McMillan Jacobs as well. So with that, I will open it up for any questions that aren't related to the software platform, because I'm not sure I know how to answer those. So.
Yeah, I was going to say, I'm happy I asked for everyone's poll before that happened. Kind of interesting timing. Okay, so we have a couple of questions here. And one of them is very straightforward from Anya. It says, the trunk looks fine. Why rehab?
Sure. Gabriel, could you go back to that slide with the cross-section of the duct and the reinforcing on it?
Yes, I can.
So the need to separate the stormwater originates from the fact that the stormwater from the Upper Plateau area was contributing to flooding in the Lower Plateau. And so the goal of this project was to separate that Upper Plateau stormwater from this Lower Plateau system. And certainly the ducts that go through the Lower Plateau here have a reasonable size to them. Where we were challenged is we needed to force this flow into the river using hydraulic driving head, and that would generate, we're also subject to varying river levels, and that's, those conditions would subject this, I guess, any conveyance of this flow to an internal pressure that could reach 9 or 10 meters of head. And these ducts, they weren't designed to withstand that. The upper corners of the ducts are fairly light in reinforcement, and pressurizing the ducts to that extent after we conducted a structural analysis of them identified that we would, as that pressure was generated, form cracking of the duct and eventual failure over time.
Our second presentation of this session is on the Groat Road Sliplining project. This project includes 4 kilometers of large diameter storm trunk under a high traffic arterial road in the City of Edmonton, which is known as Groat Road. Our presenter is Jason Lueke. A little deja vu I'm having here, as Jason has over 20 years of experience in consulting, education and research focused specifically on trenchless engineering and construction. Prior to rejoining AE in 2012, he served as assistant professor and senior sustainability scientist at Arizona State University. In his current role of national practice leader for trenchless technology at Associate Engineering, he provides technical and general engineering support across Canada for all AE offices. So a fun fact about Jason is that he has over 1,300 geocache finds, which since finding this out, I Googled it and I still don't fully understand how this hobby works. However, I can confirm that you cannot buy them and 1,300 is a lot. So on that note, please, Jason, take it away.
Awesome. Thank you, Carly. Muchly appreciated. So good afternoon and welcome to the last presentation of the day. I'm glad everyone's here, and we actually have more people now than we did before we had the technical glitches. So this is excellent. I'm glad we replicated some people. So this is excellent. So today what we'll be doing is talking about the Groat Road Storm Trunk Rehabilitation Project. And this is a project that we'll go through. It's kind of unique. Some of you know that we provide contractor services, and one of those contractors that we work a lot with is Shanghai Construction, and we started working with them back in 2013 on a tunnel up in Edmonton underneath the Anthony Henday, and we've kind of grown a little bit of a partnership there working with them, and we help them out on a variety of projects, and this is one of them. So this project here is, I guess originally started, it was a City of Edmonton project, and then Edmonton transitioned and they got switched over to EPCOR. So midway through the project, the client changed from City of Edmonton to EPCOR. The same people are involved on that side. And and then we weren't the design engineers for this. We were the contractors engineers. Stantec was the original design engineer for the City of Edmonton, and they helped, and they did a lot of the groundwork to get the project in up to tendering. And then so we got involved, Associated got involved to assist Shanghai Construction in putting together their responses to City of Edmonton's RFPs for doing this work. And so yeah, our role was more in the implementation and moving this design, taking it from design into construction. All right, so a little bit of an outline of the project. We'll give a little brief background, talk about the RFP and the tender phase, do some discussions about Part A, the design, Part B, construction, Part A design, Part A construction, Part B design, Part B construction. And they'll make more sense once we get into the background in terms of understanding how the project was divided out. So a little bit of background. So the Groat Road storm trunk is in the Groat storm basin, and this is a relatively large basin in the city of Edmonton. Encompasses approximately 1,844 hectares of area. We got some industrial areas, lots of residential, commercial. The trunk itself is about 9.9 kilometers, and the portion that we're working on was installed in the early, mid-1900s, 1953 to 1955, and ranges between 7.6 and 17.6 meters in depth. This was constructed by hand tunneling, and the trunk itself was a liner plate bolted together, multi-plate kind of configuration. Corrugated metal bolted together. The project itself, as I said before, was kind of divided up into two portions. There was Part A, which we'll get up to here on a map and show you what that means, was approximately 1.8 kilometers of 1,700 diameter corrugated metal pipes to be rehabilitated. And Part B involved 2.2 kilometers of 2,300 millimeter diameter corrugated metal pipe to be constructed or rehabilitated. The manhole connections were also a part of that rehabilitation program, and there were several drill drops. And for those that are outside the city of Edmonton, a drill drop is essentially the city of Edmonton has a lot of these deep trunks, and it's just really due to the topography of Edmonton, is that we have the North Saskatchewan River, which kind of bisects the city, and it's at a relatively low elevation. And then you have the tablelands on either side, and we need to get the stormwater from the tablelands down into the river. And so deep trunks, in the city of Edmonton is not uncommon. And again, probably a lot of you also know that the city of Edmonton at one time was probably one of the larger tunneling contractors in North America. And I forget exactly how many TBMs they owned, but the city of Edmonton self-performed a lot of tunneling work, or all the tunneling work in the city of Edmonton. And so it was not uncommon for these large diameter trunks to be installed. And just due to the topography and how it worked, we had these deep trunks in the city of Edmonton, and we have our collectors that are relatively shallow. And at various points, we're connecting the collectors down to these deep trunks. And so the way this was done, the drill drops, was they would drill a 600 or 750 diameter hole, and they would drop a pipe vertically and kind of hook it up to the bottom of a manhole on the surface, and they would drop down into the trunk. And that could be several tens of meters kind of thing to get down through these drill drop type applications. The pictures here on the right kind of show some of the configuration, or some, what are some existing conditions when Shanghai went through and did their initial construction or inspections. You can see the corrugated metal pipe. There was a lot of holes in it. That was very common. A little bit of debris were built up in the bottom. We'll get into some more of that in terms of inspection pictures here in a bit. Background. All right, so EPCOR's, or City of Edmonton's, I'm just going to say EPCOR now, because at the time it was City of Edmonton. But Stantec at that time, they did a lot of work. They went through and did the inspection of this pipe in 2012. I think it was EPCOR at that time. And they identified as requiring repair. Lots of voids were found outside the pipe due to the corrosion. Water's getting in and out and washing out a little bit of the fines around here. The soil here is a glacial till, so it wasn't too bad in terms of granular, but there were voids that were developed every so often. In 2014, 2015, there's multi-sensor inspections completed, essentially to get an idea of what the condition of this pipe was in terms of ovality. And, in general, the majority of this pipe had ovality less than 3%, which isn't too bad when you consider the age and the material here. But there were a few locations where the ovality was in excess of 5%, and that typically is not a good thing. Measured wall loss ranged from 13% to 69%, and lots of them had more than 30%. And so you can take a look here, and this is Shanghai guys. They're fully suited up doing the walkthrough. And you can see here that one of the things, and hopefully you can see it here, is that there was, the bottom of this pipe was corroded out. And so as they're walking through, they're probing to see what's the condition. In a lot of cases, there was bottom here left. A lot of the debris that went down the storm trunk would accumulate in the bottom and make it fairly firm. But there was some places where there were larger voids that had to be fixed before other rehabilitation was done. Here, where this bottom picture is the Shanghai guys going through and doing essentially a mandrel test, going through to see, because before we ordered the pipe to do the rehabilitation, I want to go make sure this pipe would fit, because eventually what we did is we did a sliplining type application, and I'll get to that here in a bit. Here's an example with the drill drop. If you can see it on the bottom picture, there's a pipe that's coming down from the crown, and that's the drill drop coming from the surface. So the background, north is to the right. If you're familiar with City of Edmonton, you have St. Albert Trail and Groat Road. You got Westmount Mall, 107th Avenue over here. The blue line represents the trunk. And then going vertically on the page, which is east-west in reality, we have the trunk going on 118th Avenue. So part A of the project was essentially everything on 118th Avenue. Part B was from the Groat Road circle down south to 107th Avenue. South of 107th Avenue, that's the city had already rehabilitated that section, and so we were tying into already rehabilitated piece of infrastructure. So almost about 4 kilometers of trunk to be rehabilitated here. Okay, so City of Edmonton, Stantec put out the RFP tender here. As they looked at various different technologies and techniques to rehabilitate this. They evaluated 14, and they also looked at replacing the trunk. They went through a value engineering process resulting in 4 technologies being carried forward: sliplining, spiral wound, centrifugally cast concrete pipe, and cured in place pipe. They put out an RFP. Shanghai Construction teamed with us, or we teamed with Shanghai, and we submitted proposals for both sliplining and spiral wound. In the end, EPCOR and Shanghai negotiated, and they end up being awarded Part A initially. And essentially Part B was contingent on the performance of the contract. And ultimately, Shanghai was successful and they were awarded midway, almost towards the end of Part B being completed. Almost at the completion of Part A, they were awarded Part B. So now what I'm going to do is talk about some of the part of our job now is that now we have the project, we're supporting our client. We needed to assist them and help develop several things in order to implement their strategy of sliplining. So now we're going to talk about some of the things that we did to support Shanghai Construction. So this was the plan for Part A. And essentially on Part A, there was a total of 4 shafts, right? We have shaft 1, which was a slide rail shaft. And from shaft 1, they would put in a sliplining rig. This is basically Ackerman makes this rig. It's a tool which essentially has some hydraulic jacks, and in the back end has almost like a big spatula that you can load in sectional pipe, and the spatula just pushes the pipe down the tunnel or down the CMP pipe. So they use the sliplining rig from shaft 1 to push pipe south, approximately 273 meters. When we get through these bends, we can't push the pipe through the bends, and so we had to do manual installation here where from shaft 2, the crews would come in and put in segments of pipe and basically carry it on trolleys and by hand into the shaft for placement. The shaft 3 was kind of in the middle there of 118th Avenue, allowing to push to the west, approximately 513 meters, and push to the east, approximately 440 meters. Okay. And then we get upward to this portion here, close to the Groat Road traffic circle, where we have to get into the situation again where we have the curves. So you can see my little red arrows down here. So there's about a 30-meter section pushed to the west, and then through the curves, approximately 91 meters. And then there's another shaft over here just to the east of Groat Road on 118th Avenue, 115 towards the traffic circle, 215 through the curve, or 265, sorry, through the curve up to this manhole. So that was a plan. And so now we're working with Shanghai to implement this solution. So one of the things that, as part of that plan was to use Hobos pipe, fiberglass reinforced pipe to do the sliplining application. And Hobos is widely used in terms of sliplining applications. But we still have to go through and do the design checks. And so using AWWA standards, we go through and do the buckling checks that can combine strain analysis, the deflections, ring deflection, pressure class, all those kind of things, and determine that the wall, what the wall thickness of pipe we need to actually use for the relining of this sewer. Part of that design process, though, is understanding that insulation process. And there was a grouting program that needed to be done, because once you get the pipe in place, you do have to grout it in place. And so part of that design was incorporating what the grout pressures would be, so we don't buckle the pipe. And so that was a very important component of that operation, or above that design. Here's some couplings, and then the jacking loads are also calculated, because if we're using the machine, we have to push this pipe in, and Hobos, the fiberglass pipe, is a jacking type pipe. You can use it for microtunneling operations as well. So again, it's a routine type insulation. For a sliplining application, the fiberglass pipe is a lot thinner than it would be for the microtunneling operation, because we're not pushing a microtunnel boring machine on the end of our pipe string. To get the pipe into place, the corrugated metal pipe is a little bit like Velcro. It doesn't allow you to push things through it very easily with all the corrugations and the bolts sticking out. So we had to devise a plan, and I think it was through a little bit of value engineering, we came up with the idea with Shanghai, or I forget who it was, about putting rails. And we have put rails. We designed rails that could be essentially, I forget what the length of these were, but they're assembled in pieces that the Shanghai crews can carry down into the tunnel, put together, and this would essentially form a stable base to allow the pipes to be pushed or to sit. They would keep all the pipes in line with each other, nice and straight. And then also a trolley was made that would ride the rails, so to speak, to assist in placement of the pipe. So this is what our structural engineers did, is figure out what these rails would be, come up with configurations, how to put it together. And of course, with the corrugations, what kind of helped, as you can see here in the cross section, is that the rails just sit on top of the corrugations, and when you do the grouting, the grout would still be allowed to kind of get around underneath the pipe. And we also put in air holes, and it was almost like a ladder that was devised and laid down to still allow the grout to freely get around all the FRP on the grouting insulation. Additionally, there were curves, and on the drawings, the curves looked relatively continuous, but in reality, they were basically, I think it was like 15-degree bends, very discrete, and so there were some issues there. And so, the team kind of implemented using 3D scanning to go through the tunnel, so we can get an idea of what that looked like, and then that was translated into a civil 3D kind of package, where Mr. Lamont and Stuart in our Edmonton office, they devised a lay schedule essentially, so that they could put together what lengths of pipe were needed. And I think it was like 300, 600, 900, 1200 lengths of pipe were cut. And so every piece of pipe going through this tunnel was put in a particular location, when it was put in by hand, so that we can make joint deflections work around some of these bends. There were some specific pieces you can see here. I think this was a specific piece that was ordered from Hobos. It came with a bend, but where possible, we would cut the pieces of pipe to allow joint deflections to occur, as opposed to put in fabricated bends. Construction in Part A. All right, so getting off to start. There was a lot of, part of that was to get in and clean the pipe and get it prepared. And so you can see here, this is one of the conditions here is looking at the amount of debris that's in the bottom of the pipe. A lot of this was flushed out. There was a company out of Winnipeg that came out, Unijet. They got some very large equipment, high volume, high pressure, and they were able to flush the majority of this out of the tunnel, or out of the trunk. But I mean, some of it did have to be hand bombed and taken out in buckets, just because of the large volume and the larger debris that was still in the tunnel. Once that repair was done, you can really get an idea of what's going on at the invert. And the design had a multi kind of step. There was a invert paving type operation, so that I can kind of get this the size of the pipe locked in and get a nice stable base to work on. Then there was void grouting, so that trying to grout the void between the CMP and the soil. And then there's the annular space grouting, which would be the grouting between the FRP and the CMP pipe. But here's just an example of the condition. I don't think all of it was like this, but there's definitely some locations where the bottom of the pipe was absent, and then this had to be filled up with the pavement. It was just concrete, quick set concrete to just lock everything into place. In some locations there were voids, and gravel was brought down with some geotextile fabric to kind of make a stable base before the grout pavement was put on top. Here's pictures kind of just showing the rails going in. You can see the rails being stacked up here at this is shaft number 3 on 118th Avenue. You see the rails stacked up and being ready to be inserted, and then you can see how the rails looked inside the tunnel. The rails periodically in the middle, they had a couple spikes that would be driven through the CMP to keep it in place so it wouldn't move. And this is where the pipe would sit, and this is how the trolley would ride on the rails to deliver pipe. So here's kind of the design. The initial design from the tender was with the grout pavement, or not the grout, the pavement here of the void. What am I trying to say here? Invert paving at the bottom. All right, and then we'd come in, and then we'd have this configuration doing cross sections every 8 meters of 6 injection ports to grout, put grout in to fill up voids that were around the pipe. And then we'd bring the pipe in and then grout the annular space between them. So there's just a picture here showing what the grout system looked like. There was inspectors on site that would periodically have to put more grout ports in to, especially if there was a lot of holes in the pipe. The Shanghai guys went through and kind of patched the holes best they could. But there's a lot of cases, there's just so many holes that as you're doing the pressurized grout, it would just be coming in everywhere. And I forget off the top of my head what the pressure of the grout was, something that I think was like 7 or 10 psi. But it would be coming out all over the place just because of the holes. So here's part A. This is shaft 1. You can see the machine. This is the Ackerman machine here. You can see it down in the shaft. And then you got the full-length Hobos pipe being loaded, and you can kind of see the spatula, as I call it here. That would just be a pushing frame that would push the pipe down the tunnel on the rails. Okay. So part A went through, and I think projects was at, trying to remember the time here. I think it was about 2019, I believe, when part B or part A finished, and they started on part B. So part B has been going on for about a year and a bit. So part B was down from the Groat Road traffic circle going south down Groat Road to 107th Avenue. This was done with a series of working shafts. We had working shaft 5, 11, 14, 15, 16, 17, based on manhole numbers. There's other manholes that had to be rehabilitated along the way. But part B was just because of space restrictions. There was traffic issues trying to work within, minimize the lane impacts. The decision was made that all of this pipe here, approximately 2.2 kilometers, would be hand bombed. And so this is what, 1,800 diameter pipe, more or less. And that would be put in by hand from these shafts. And you can see, so from shaft 5, it was pushed to the north, through the south, through the bends, through this bend here, again, north and south. And so that was a plan. And in order to do this, though, I'll show you some stuff we had to do, but this here is the Part B inspection. So after Shanghai was awarded, or the plan to award Part B to Shanghai was kind of made known. Shanghai went through Part B and did a visual inspection again. They had a portable man drill that they brought through to, again, just make sure that the pipe that was going to be ordered would fit through. And there were some areas of concern. You can see a little bit of settlement here and some ovality issues. Here's a picture of a drill drop, so the pipe has actually slipped down, and I forget the exact location where this was, but I mean, obviously there could be potential for voids up here that had to be addressed. And then this here is just kind of a realignment, and I don't know the exact nature for it, but I suspect that because this was a tunnel installation, maybe there was tunneling from the north, tunneling from the south, and then it just didn't quite line up. So there was a little bit of a transition where this couldn't be slip lined through, and a shaft had to be put here specifically to allow a prefabricated joint or a fitting to get in here to make that transition. So again, this is the entire length from the Groat Road traffic circle down to 107th. And again, we put together a lay schedule all the way through to determine, where these pipes would be sitting. We can see here, there was pipes that were cut to be 1.5 meters, 0.4, 0.9. We had prefabricated bends and different angles, right? And then so we developed a lay schedule for the entire length around here. And then that's what Shanghai used to follow and put that pipe in place. A little bit different approach was used in Part B, knowing that there was a lot of issues in trying to do the grouting with all the holes in the pipe. We went through and did the pavement here. Now we go into the grouting. A little bit different approach, knowing that before we had a lot of issues with the voids in the pipe. I'm going to talk really fast so we can get through this. A lot of voids in the pipe, and so we came up with a little bit different approach. Put the rails in the invert paving, and then put the pipe on top, and then we would actually grout in segments, and then the segments would vary upwards of 10 to 100 meters kind of thing, and basically to construct bulkheads and do pressure grouting. And so in this, and we developed a table here that would allow Shanghai to figure out what pressure they needed to actually allow the grouting to take place. And the grouting here was through this process, we're able to pressurize that annular space, and it would push a grout out into the voids outside the pipe. Periodically, I think Shanghai had to go in and maybe make some holes where the pipe was in good condition. In a lot of places, the pipe there was enough holes there to allow the grout to get out. And this here I think was just a little bit more of maybe a more elegant solution kind of thing in order to make this work. So yeah, a little bit of a change in Part B. Again, there was other things we had to do in terms of putting together manholes, structures, and some structural design. So this here is a particular, I forget which manhole this is. I want to say it's manhole 10, but I might be wrong. So there was some drill drop replacements, and so and there was some definite issues in terms of trying to do bypass on a trunk this large, and especially where there was access points. And so the idea here was to design these perched manholes so we can do the rehabilitation, do the grouting, then come back in and build these manholes, T-risers essentially, over top of the pipe. So you can kind of see here the configuration, and it's kind of a weird configuration because there's shafts here. And in order to make this work, we had to do a little bit of undermining of the shaft to allow space for the concrete placement here and this wedge to be in here to get on some kind of firm ground. So we did a few of these along the way, so some custom structural design. Part B, construction. You can see here going down a liner plate shaft, putting in some pipe. This here's a larger diameter hole boss pipe. You can see that coming in. Due to the workspace restrictions, there was some issues in terms of staging, so pipe was brought to site every day, staged so that it was just in time delivery, so the pipe could be installed and we're not taking up a large space to do work. Here we can see sliplining, we can see the tugger going in there to put the pipe in place, and so all the joints had to be pulled together to make sure that they were sealed. All the joints on the whole bus pipe had gaskets. Here you can see some of the blocking required before the grouting. All right, so all the pipe was blocked in place, and then the blocking was left in place, because obviously once you're doing the grouting, the issue would be flotation. And so with the blocking in place, we could do the pressurized grout, and that pipe would be locked into place and not start floating on us. All right, here's the annular space grouting. So you can see here some of the grout lines coming in, and they, based on what the length of the tunnel, the elevation difference, we would know what pressure we need at the crown so that we can get more than the original design pressure for the annulars for the void grouting and not collapse a pipe. And I think we got up to about, I think a spring line we're averaging, was it 7, 8, 9 PSI kind of thing. And that would get out into the voids and give that stability on the sides to keep everything structurally sound. You can just see some transitions here and some of the finished product at the end. So that concludes the presentation. Just a few acknowledgements here. Shanghai Construction, our client on the project. EPCOR would be the overall client that Shanghai is working for. And then from Associated, we got Chris Lamont, lead project engineer, Linda Chaco, Tyrell Stang doing a lot of surveying, Sam Saunders, Keaton Thompson, Deshanka, Caitlin, Mike Polson. Large effort here to get everything working together. So that's it. Is there any questions?
Sure. Well, let's start with Blaine's question.
Sure. What's Blaine's question?
Jason, how did you deal with the sections that were so out of round that the replacement piper would not find?
Oh, the replacement pipe may not fit. There wasn't many locations actually where there was an issue. That was part of when Shanghai went through and did the initial walkthrough before ordering pipe. That they're able to kind of just do a mandrel test essentially to make sure that the pipe would work, right? So that was done to make sure that through those locations, and then the pipe was ordered so that it would fit through those tighter locations. The good thing about this that a slighter or a diameter reduction was allowable just because we're moving to a much smoother product in terms of the fiberglass, in terms of its just resistance of flow compared to the CMP product. So even a smaller diameter is still able to maintain the same flow capacity in a larger diameter corrugated metal pipe.
Okay. We also have a question from Anya that says, was increased flow velocity not an issue for the storm system?
You're right, there would be an increase in velocity. I do forget we had those discussions a couple of years ago and identified those as potential issues. I believe through the design there originally, that was accounted for. We were tying into a downstream system that was already rehabilitated, and I think and we don't have any pictures of it here, but I saw some pictures recently here because we were tying in the downstream end at 107th, and you can look down and see it's a smooth concrete cast in place concrete liner. And so that would have an increased flow capacity as well. So I think everything downstream of us was already rehabilitated and ready to take on that additional flow as a result of the velocity increase in the pieces that we were rehabilitating.
Maybe one more question, because we'll have to have a little time for closure. Yep. We could take Anya. How many lifts was grouting done? And how many lifts was grouting done?
So depended. In part A, it was done in lifts, and we'd be doing hundreds of meters at a time. And the lifts were designed to prevent flotation. So we were doing calculations to determine how much grout could be added before the pipe started floating. And so it was done incrementally between bulkheads. In part B, it was done by pressure. So we determined where the bulkheads had to be. We designed bulkheads to take on the pressure required for grouting. And I forget what the average length of these bulkheads were. It was like, I want to say somewhere between 40, 60 meters kind of thing, depends on where we were. We'd be doing that in segments, and we could pressurize grout those blocks or those sections. And then there was no issues. It was just to grout the entire section as in one piece. Going back to the gravity grouting type application in lifts, in the end, there was a QA program in place to check to make sure there's grout all over the place. We drilled holes, hammer tests, those kind of things. And then also in those places where there was concerns, once the pipe had a good amount of grout around it past the spring line, we were able to do some pressure grouting in certain locations so that we can make sure that all those voids are filled. On the downstream part A or part B, sorry, the grouting program also included a little bit of a QA in there that we would want to make sure that we maintained a certain pressure for, I forget what the duration was, just to make sure that there were no voids, that all the voids are filled and the grout had time to kind of permeate into any kind of voids that might have been outside that pipe.
Okay. Well, I guess what I'll do is good for questions. So. We got a lot of votes on this one. We got 8 likes. Okay. We never got that all
it's Paul
day.
Didlick. Okay, what do we got?
Okay. So Paul Didlick. On Trenchless projects, we receive a lot of comments from the public that we are always just standing around, when actually we are doing a lot of work just underground. On a project, Groat Road, being in such a high traffic location, did you encounter this, and did you do anything to mitigate the perception?
Well, Paul, that's an excellent question. I appreciate you bringing that out, and this, I think this hits on a couple points. A lot of you guys in the office think I don't do a lot, but I'm actually doing a lot of trenchless stuff. So you can see that standing around is kind of where it's at. I don't, there definitely was a lot of public communications going on, but EPCOR did a lot of the public communications to kind of get everybody out there. I think what kind of helped in this situation was that for the last, since, February of this year, there wasn't a lot of traffic out there. And, I don't think in the last 7 or 8 months there was a lot of issues in terms of complaints from residents regarding us looking around. But, I don't know if I've ever experienced that personally, but I can definitely see the perception. So.
Perfect. And I will hand it over to you, Jason, to do the wrap up for
Awesome.
the day.
Well, you know what, guys? Everybody, thanks for still being here. Sorry all the technical issues, but I'm glad it's just at the end of the day. So let's see if we can get to the end here. So yesterday, when we kind of started, I gave a presentation to the AE staff, and in terms of what I wanted everyone to take away, and I thought it'd be good to kind of go through this again. And one thing here, I hope that everyone that attended, and AE people, and even our clients, is that there is a design process that we go through for all of these projects, and especially in trenchless. If it's microtunneling and directional drilling, there is a design process to follow, and it's a standard approach. Some of it has there's published regulations or published guides in terms of best practices that we should be following, and so we should be using those. Lessons learned. I think we went through a lot of lessons learned here, and hopefully everyone took away a little bit in terms of how we can do things better. Yesterday afternoon, just at the AE staff, we had some more candid lessons learned about what we could be doing better on trenchless projects, and today that we hit on a few as well, especially maybe like Kean's the boulder claim issue. I think that's a really good one for all of us to keep in mind in terms of unique ways of dealing with things. Day two, it was with our clients, and this is something that we hadn't done before, and I hope it worked out well. I mean, this wasn't something we planned for at the beginning, and realistically, I'd be happy if we had 30 or 40 people show up, but I think we had a lot, so it was great that everyone had an opportunity to come join us. And again, it's not something that we normally do, but hopefully it was appreciated, and you guys learned a little bit about us, and learned a little bit about what trenchless can do for you out there. Internally, I want to make sure that our staff understand what our capabilities are, so that we know what we're able to do. We know what kind of projects we've done. I am hoping that we showcase there's a lot of opportunities for our staff to get involved with some really unique projects along the way, as well as we talked about technical societies yesterday. So don't be shy to get involved. And if you have any questions, definitely come ask me, or I can help you out. And the other one here is for our internal staff is the opportunities across market, and so knowing what we can do internally. If you see opportunities and you have a client that needs help, hopefully you can patch on to one of the people here that you saw the past couple of days and help things out. And if all else fails, get a hold of me, and I can definitely hook you up with the right people. It's all about making sure that we can serve our clients and show and help them out where we can. So that's what I wanted, just the takeaways from yesterday. So hopefully that was all demonstrated throughout the last 2 days. And then thank you to our clients for joining us. We hope in sharing our experiences and insights with you, you have the opportunity to, and you had the opportunity to meet some of the associated team, as well as some other colleagues across the company. We'll help them just keeping our long-term relationships together and make future collaborations better. So in closing, I'm going to say stay safe and keep well. Again, everyone, thanks for joining us. If you want to talk to me directly, there's my email address and telephone number. Give me a call. I can hook you up with anybody you need to be hooked up with across the country. And if you just need a chat, I'm here for that as well. So again, thank you very much for joining us today. And I hope you had a great event. We'll talk to you all soon in the future. Thank you.